Welcome, Chem Honors people. Molecular Structure, Chapter 13, and that's a picture of me being all frustrated because I keep making mistakes, like the mistake I made uploading the test for the A-Day class, today actually. Um, you know, trying to get used to new stuff. So I'm going to get right into this because I don't want the video to run too long. Chapter 13, let's go to notes. The behavior of molecules based on the structure of its bonding. So biopeople, what that means is shape determines function. And so the shape of the molecules determine the type of reactions and reaction pathways that it can undergo. So therefore the shape of the reactants determines the type of products that you can get. How it interacts in the body, how it interacts with other molecules, all of this is very important. They start off by introducing Lewis dot diagrams, and they say, okay, Lewis dot diagrams are diagrams which show the valence electrons and how they fill the outer shells. That's fine, but really what I think is better to understand the limitations of Lewis dot diagrams. There are a lot of different ways of diagramming molecules. Lewis is only one way. There are things called Hawthorne projections and Newman projections, lots of different ways of showing different aspects of a molecule. Lewis structures are really only good at doing two things. They're good at showing the actual geometry of the molecule. In other words, its shape. And they are good at predicting the polarity of the molecule. Is it polar or non-polar? And that's it. If you try to use Lewis dot diagrams, for instance, for three-dimensional arrangement of things, something we call chirality, then you're not going to do well with it. They're just not designed to do that. They're two-dimensional rendering, and they're a code for three-dimensional shape, so it'll allow you to predict the shape, but it doesn't allow you to actually see the three-dimensional relationship. So there are limitations to Lewis structures. For all atoms that form covalent bonds except hydrogen, 8 electrons represent, well, that's called the octet rule. And so Lewis dot diagrams are really good for octet followers. There are some octet violators that we can deal with Lewis structures, not just hydrogen. Now, hydrogen is a Lewis violator, an octet rule violator, because you only need 2 electrons to fill up the first energy level. So let's take this down. We have octet violators and number of electrons needed for stability. And this, of course, is in a Lewis diagram. Well, we already said hydrogen's an octet violator. It only needs 2 electrons to be stable, and that's because you're only filling up the first energy level. So helium is also an octet violator. It only has 1 energy level, 1 shell, the 1s shell, and you only need 2 electrons to fill it up. The next 2 elements, boron and, we'll skip lithium because lithium's ionic. Lewis dot diagrams. You can do ionic with Lewis dot, but the thing with ionic compounds is when lithium goes to bond, it loses its outermost electron, and what you're left with is a noble gas core. So we don't generally use Lewis dot diagrams for ionic. You can, but we usually use them for covalent. So we're going to skip lithium. Beryllium would be the next element that's an octet violator, and it only needs 4 electrons to be stable. I'm going to write or 8 electrons, but here's the thing. Beryllium is so small of an atom that it is really more stable when there's only 4 electrons in its outer shell than when there's 8. And boron, same thing, very small atom. It's very good at accommodating 6 electrons, so it's most stable when it's actually 6 electrons, but it can also accommodate up to 8 electrons. Put a little star next to it because when it does 8 electrons, it's no longer a octet violator. The only other octet violators you have to concern yourselves with are 2 things. What's called an expanded octet. And things that have expanded octets are ones that can accommodate more than 8 electrons. We're just going to write more than 8. And that's because they have d orbitals. So anything in the third period or below third period elements can do expanded octets, and therefore they can accommodate more than 8, so they violate the octet rule. And the last one is any molecule with a total of an odd number of valence electrons. This is going to write VE for valence electrons. Okay, in a Lewis dot diagram, the bonds work in pairs of electrons like we did in chapter 12, and it doesn't matter whether it's a coordination bond or whether it's each atom contributing one electron. Anytime there are two electrons in between atoms bonding them together, we're going to call them shared electron pairs. And if the electrons are in the outer shell but is not involved in any sort of bonding, we're going to call them unshared electron pairs. So everything works in pairs. To make a Lewis diagram, you have to follow these steps. Now, it was in the other video last week, but I would learn the steps. You have to go through them in order. A lot of the Lewis structures that you've done before are all octet followers, and so you found the central atom and then you just put electron pairs all around it. That process won't work for you here. There are a lot of octet violators to deal with, and in order to get it right, you have to follow the process in order. So step 1, you add up the number of valence electrons for each of the atoms that make up the molecule. So these valence electrons, they're your budget. You have to use that many electrons. If you add up in the molecule that there's a total of 10 electrons, then you have to use all 10. You can't use 12, you can't use 8, you have to use 10. And it is this budget of valence electrons that dictates the geometry and the polarity of the molecule. Every time you bond an atom together, subtract 2 electrons. And then what you're supposed to do with the electrons that are left over is you're supposed to use them to complete the octets on the atoms that need octets. 2 problems that you can run into. If you don't have enough electrons to complete the octets, then you can go back and do what's called a double bond or a triple bond. Now, a double bond, a single bond involves 2 electrons. So a double bond we write with 2 lines, and that involves 4 electrons. And a triple bond between atoms would involve 6 electrons. There is no such thing as a quadruple bond. We'll find out in more detail the difference between a single, double, and triple bond. But for now, it's just the number of times the atom overlaps. If it's a single bond, it overlaps once, so therefore there's 2 electrons. In a double bond, you have 2 different overlaps at the same time. That involves a total of 4 electrons. If you complete steps 1, 2, and 3, and then you have electrons left over, then you're going to expand the octet. All right, so let's try a couple of these. First of all, octet followers for the most part. We'll do these 3 as an example. These are pretty easy. Okay, so the first one, hydrogen telluride. So H2Te. Now, as far as figuring out the valence electrons on these things, you can write out the configurations for each atom, but there's really a pattern here. The group 1 elements, they have an S1 configuration, so therefore they only have 1 valence electron. Whereas group 2 has an S2 configuration, so 2 valence electrons. Now, group 13, or what I like to say is group 3-teen, has 3 valence electrons. Group 14 has 4 valence electrons. Group 5-teen has 5. Group 16 has 6. Group 17 has 7, and then the noble gases would have 8. So in group 13, you're looking at an S2P1 configuration. That's where they're getting the 3. In group 14, you're looking at an S2P2 configuration outside the core. So that's where they're getting the 4. But again, it's easy to remember it. The main group elements, 1 valence electron for group 1, 2 for group 2, 3 for 3-tene, 4 for 14, 5 for 5-tene, etc. All right, so we'll come back to our little example. First thing I'm going to do is my budget. So valence electrons, 1 for each of the hydrogens. So 1 valence electron times 2 hydrogens plus 6 for the tellurium. That means I have 8 electron dots to work with. Now, as far as choosing what's called the central atom, if you've done the Honk lab in biology, hydrogen, oxygen, nitrogen, carbon, one thing I like about the Honk lab is it teaches you the normal valence of things. In other words, where it's most stable. Hydrogen and halogens tend to form one bond. Oxygen tends to form 2 bonds. Now, there are exceptions, but it's most stable when oxygen forms 2 bonds. Same thing with nitrogen, forms 3 bonds, and carbon tends to form 4 bonds. But there are lots of exceptions. This is where it's most stable. So when you talk about atoms, there are 2 types in a molecule. There's what we call the central atoms and terminal atoms. And the only difference between the two is that in a central atom, that atom is bonded to more than one other atom. So central doesn't mean right in the middle of the molecule. Central can be towards one side of the molecule or the other if it's a large molecule. It has more than one atom connected to it, whereas a terminal atom is only bonded to one other atom. So on a test, you have this hydrogen telluride, right? So you have to decide which one's going to be the central atom, which one's going to be the terminal atom. And for me, it's a pretty easy choice because the hydrogen can only form one bond. Therefore, hydrogen and halogens can never be central atoms. So we're going to put tellurium in the middle. And I'm just going to spread the hydrogens out. Now, Lewis structures, the position of things are just like when we did electron dot diagrams. We put something to the north, something to the west, something to the east, something to the south. Okay. We're going to connect these with a single covalent bond, and that's going to use 4 electrons, which is going to leave me 4 for my octets. Now, the hydrogens don't need octets. The tellurium does. So I'm going to add those 4 electron dots north and south to the tellurium, and then that's my Lewis structure. The next one, nickel triiodide. I'm sorry, nitrogen triiodide. Again, let's start with our budget. Valence electrons, nickel, or I keep saying nickel, nitrogen's in column 15, and iodine's a halogen, so it's in column 17. So we'll do 7 electrons, but there's 3 halogens. So that gives me a total of 26 electrons for my budget. So which one is going to be the central atom? The iodine is a halogen, and halogens can only form one bond. There are some exceptions, by the way. The bigger the atom, the more likely it is that it can form more than one bond. So iodine and bromine can be exceptions, but we're going to put nitrogen in the middle, and we're going to surround it with the 3 iodines. That is going to use up 6 of my valence electrons and leave me 20 to complete my octets. Each iodine needs 6 more electrons, so that's going to use up 18 of the 20. And then the last 2 I can put on the nitrogen to complete the octet. So there's my completed Lewis structure. And then the last one was carbon tetrabromide. so again, we do our valence electrons. 14, group 14 for the carbon, group 17, but there's 4 of them for bromine, so that's a total of 32 electrons. We'll put the carbon in the middle and connect it to 4 bromines. Now, technically what I'm drawing is not a Lewis structure. It's something called a Kekula structure. And Kekula is the scientist who came up with this. He's the guy who changed the Lewis dot diagrams and substituted the bonds for single lines and double lines and triple lines. Technically, a Lewis structure, you would have to draw it like this. 2 dots connecting each of the bromines. I'll accept either one. I'm an organic chemist. We use Kekula. We don't really use Lewis structures. But let's say you were taking a standardized test. You take the achievement or the SAT-2 achievement test and chemistry, and they ask for Lewis, then you have to do Lewis, not Kekula. But I'll accept either one on a test. All right, so we've got 24 electrons left over, and each of the bromines requires 6 more electrons, so that works out perfectly. And there's our structure for carbon tetrabromide. So I'm going to stop the video here and then pick up with the octet violators, the multiple bonding, and the expanded octets on the next video.